In this video, we are going to look at integration of standard trigonometric functions. And we are going to use the fact that integration reverses the operation of differentiation. In other words, if I know that 2x is the derivative of x squared, then I know that integral of 2x dx is going to be x squared plus c. You can check, if you differentiate x squared, you are going to get 2x. In general, if a function f dash x is recognized as the derivative of a function f of x, then integral of f dash x dx is going to be the function itself plus constant. For example, if you know that the derivative of sine x is cos x, then using the fact that the integration reverses the process of differentiation, right? So you will know that the integral of cos x dx is going to be sine x plus a constant. In the same way, if you know that the derivative of cos x is minus sine x, and that the integration reverses the differentiation, then you will know that integral of sine x dx is going to be minus cos x plus c. Look through the other standard trigonometric functions, their derivatives and their integrals. You don't need to remember these integrals. If you know their derivatives, you always will be able to write the integrals. Alright, we are going to use now these facts to look how to solve a little bit more complicated trigonometric functions. So we can solve the following integrals by considering the corresponding differentiation. So we can show that integral of a constant multiplied by cos x dx is going to be c sine x plus a constant. That is because if you will differentiate c sine x, you are going to get c cos x. In other words, you take c, the constant, out of the integral. Okay, so here's another integral, cos of ax plus b dx. Again, the derivative of 1 over a sine ax plus b plus a constant, of course, is going to be cos of ax plus b multiplied by the derivative of the internal function, which is a. So to cancel that a that we have to multiply, we're dividing by a. In the same way, we can see that integral of 3 sec squared x dx is going to be 3 tan x plus k. You can check it by differentiating the result and you will get the function under the integral. And the same is true about all other examples that you can look through more carefully by pausing the video so you can see in detail how it's been done. Always by differentiating this result, you can see how you can get the function under the integral, and that's how it's been done in the first place. In fact, that is not the only way how you do it by just kind of guessing and adjusting your differentiation. There is in my opinion, even better method, and I will show you in a minute how to use substitution instead of guessing if you struggle with this, right? So let's see some examples. Here are some examples for you to try. I would like you first to pause the video and try to solve the below questions yourself. And after this, check the answers. Here are the answers for the questions that I have offered you. So here's the first example. Integral sine 2x dx is going to be minus half of cos 2x plus c. I have to introduce this half to compensate for 2, which will appear after differentiation cos 2x. I have promised you a different method of solving these questions, and this method is called substitution method. Here is my example again, sine 2x dx. But now, since I know that my argument here is 2x, I can change my argument. In fact, the argument was x. Sorry. So I can change my argument to 2x. Look, when I will change my argument to 2x, once differentiated, I should divide by 2 to compensate for that 2 that will appear after differentiation. Okay, so now I have, in other words, I can kind of introduce another variable u, which is 2x. Okay, therefore du is going to be 2 dx, and dx therefore is going to be du divided by 2. Replacing my dx with du over 2 and 2x with u, I'm going to get sine u du divided by 2, or sine 2x d 2x over 2. And of course we are getting minus half cos 2x plus c. Alright, here's another example. 3 cos 4x minus pi over 2 dx. Again, derivative of 3 sine 4x minus pi over 2 is going to give me 3 cos 4x minus pi over 2. Only I have to count for this 4 in the argument of sine. So I have to divide by 4 plus a constant. Using the substitution method, you can see how I'm changing my variable here. I change it to 4x minus pi over 2, and I divide by 4 to compensate for this 4 appearing after differentiation. And so I have now 3 cos u du divided by 4. 3/4 will go out of the integral, and cos u du is going to give me sine u, where my u was 4x minus pi over 2 plus a constant. In the same way, you can see the answers to other examples that I gave you. Please check your answers and other examples here. That's it. Thank you for watching.